Hi there, this video is about a review and a teardown of the Kyweets AT118A multimeter. As a disclaimer, Kyweets sent me this multimeter for the review but did not pay me or sponsor the video, and before accepting the item for review I clarified that I could tell it all, good or bad, to which Kyweets agreed. Yet, since I got this $36 meter for free, I marked the video as a paid promotion. It came from Kyweets' Amazon store in this package. Let's see what we've got. A manual that looks actually quite decent. Certainly I've seen much worse in meters of this price range. A box with accessories, a set of two AA batteries, extra heavy duty, a thermocouple probe for temperature measurements, and a set of probe leads that look quite decent and are surprisingly heavy. Again, a nice surprise compared to what you get with other budget meters. And of course the meter itself. It looks quite rugged, which is probably because of these angles in the design instead of the more traditional curved outlines. Let's add the batteries to give it a brief spin before the teardown. As usual, the battery compartment is behind the tilting bale. The screw for the battery compartment is metal threaded. Nice. But unfortunately the fuses are nowhere to be seen. That means for a fuse change you will need to open the whole meter. With the batteries installed, does it turn on? It does. This is kind of cool. When you select a range, the terminals you are supposed to use blink briefly in green. I guess that may come in handy for inexperienced users, but it won't stop you ignoring the hint and leaving the leads in the wrong terminals. The backlight is nice and even, and I like that it's not turning off automatically. If you press the button longer, you can enable a torch light that might come in handy in some situations. In fact, the AT118A has even more light effects. If you start getting into what the manufacturer thinks dangerous territory, the backlight turns on automatically, but in red. For voltages, that threshold is 80 volts DC or AC. And for currents, it's 1 amp. You can't turn that danger function off, which means battery life is going to reduce if your measurements lay often in the danger zone. Let's have a closer look inside. To gain access, we obviously need to remove the sleeve first, and that proved to be quite a tough job. I'm showing this at a fast speed because it took me quite a while. With the sleeve finally removed, there are 4 recessed screws to remove. These turn out to be self-tappers, as it's common these days. Once the screws are all out, the 2 halves can be pulled apart. There is a white LED at an angle. This is obviously for the torchlight function. The PCB contains springs that connect to pads on the battery compartments in the back shell. That's quite a nice solution because it allows easy connection to power the meter when the back is open, far better than the reverse arrangement with the pads on the PCB and the springs on the battery as in the Uni-T UT210E clamp meter, for example. On first impressions, the PCB looks quite clean and organized. I want to have a look at how they implemented the lights to show the correct terminals for each range, and for that the PCB has to come out. It is held with a couple of self-tapper screws. On separation, the LCD stays in the housing. That white thing attached to the PCB is actually the backlight. Quite clever. There are 4 light pipes that lead to each of the terminals. And here's the PCB. We can see the 4 LEDs that drive the light pipes. The socket inserts look a little bit fragile, but at least they will be easy to repair. The hand soldering of the bigger components has left quite some flux residue. On the component side, we have an inductor in the upper left corner, probably some boost circuitry for the backlight voltage. There are 3 wires going to the backlight because this meter has a 2-colored backlight. The actual brains of the meter is hidden under the blob, and there is the standard EEPROM for the calibration values. There are no trim pots of any kind. Further down, we have the unusual feature of an SMD current shunt of 5 milliohms. Not sure if that is a good idea, because at 10 amps this little fellow will have to dissipate half a watt and will get very hot. The usual bare metal bar as a shunt can handle that much better and also cool down much faster for repeated measurements. We have only 2 green PTCs as input protection and just 2 smallish resistors in series to handle the high voltages. One side of the 10 amp fuse holder is not seated properly. Let's have a closer look at these fuses and get them out. The 10 amp fuse is a 6.3mm by 32mm ceramic type, and there is nothing written on the ceramic body itself. According to the manual, the other fuse is supposed to be 600 milliamps. It's the same size as the 10 amp fuse and with an equally blank body. One of the end caps has an engraving, so at least we know this fuse is a 10 amp 250 volt type, claiming to be UL listed. It also has a marking 613B, not sure what that means. If anyone knows, please leave a comment. The other fuse has the same marking and shows 600 milliamps 250 volts. To find out if these no-name fuses actually contain sand for arc quenching, I compared their weight with a branded CBAR fuse of the same size. As I don't have a decent scale with enough resolution, I came up with this simple method with a CBAR fuse on the left. It looks to me as they have near enough the same weight. With the back off, it's easy to measure the HT118's power consumption on the red BM869S. After an initial jump caused by all the blinking lights, it settles to just below 3 milliamps, but there is an AC component of 7 milliamps as well. Turning the backlight on increases both to about 15 milliamps DC and 24 milliamps AC. To investigate this AC current component, I decided to look at the voltage drop across the resistance inside the BM869S milliamp terminals. Hence, what we see is actually current. There is of course noise, but when I turn on the HT118, you can clearly see the spikes, and with the backlight turned on in addition, their frequency increases. These must come from that boost converter we saw earlier in the teardown. The current consumption in the ohm and continuity mode is a bit higher, 3.3 milliamps, but shoots up significantly when touching the probes. Not only does that activate the beeper, but also an additional red-green LED above the display. And of course, if the danger backlight kicks in, the current increases from 3 milliamps to almost 20 milliamps. And if I turn the normal backlight on as well? Well, it's smart. It doesn't add to the power consumption. Of course, once the danger is over, the normal backlight now kicks in. Okay, and before I forget, using the torch function will increase the current to almost 20 milliamps DC, and torch together with backlight clocks in at almost 33 milliamps with an almost equal AC part riding on top. And with that, I finally put the meter back together for some usability and accuracy tests. The HT118A has a tilting bail that looks quite well designed compared to many cheaper meters. You can turn the range switch easily without moving the meter. When tilted up, pressing the button in a stabbing action causes the meter to slide backwards. You quickly develop the habit of grabbing the meter, supporting it from the rear while using the thumb to operate the buttons. The leftmost Funk button changes between AC and DC and selects between ohm, continuity and diode mode. Sadly, the HT118 has no manual range function. The usual hold button is there, and as useless as in most other meters because it just freezes the display when pressed. I don't remember ever actually using hold in any multimeter. The max min button on the other hand is actually quite useful, because you can use it to measure something where you need to concentrate to put the probes in correctly without a chance to turn your head to read the display. If you hold the func key while turning on the meter, the automatic turn off after 15 minutes is disabled. Strangely though, the meter will still give you the usual warning beeps when the 15 minutes have elapsed, it just doesn't turn off afterwards. The case itself is sturdy and it feels solid enough. As I mentioned already, the test leads are a step up from the usual nasty ones you get with cheap meters. The HT118A leads feel quite well made. It's not silicon isolated wires, mind you, so you better stay clear of any soldering irons, but not bad at all. The HT118 has a bar graph, which is not common for meters in this price class, so let's check its responsiveness using a triangular wave going from 0 to 5 volts and back to 0 in 0.1 Hz or 10 seconds. No problems, of course. Changing the frequency to 0.5 Hz or 1 second rise and 1 second fall. Still works fine. Changing to 1 Hz, we can see that the bar graph in the HT118 is now too slow to reach the full range anymore. 1.5 Hz, 2 Hz. At 2.5 Hz, the HT118 can no longer show that we have in fact an AC signal and its bar graph has stopped moving. Here are the specs from the manual that came with the Kyweeds meter. I have to stress that because you search for HT118 and you find meters of this type looking very similar are sold under many names, but I found that the published accuracy specs are not always the same. For example, compared with a seemingly identical meter online, the Kyweeds has a slightly better AC voltage spec but a worse spec for DC and AC currents. With that said, the specs are what you can expect from a meter of the $30 to $40 price class. The DC current accuracy is a bit disappointing though. Anyway, usually the meters are much better than the specs. Let's see if that holds true for the HT118A as well. For most of my tests, I compare the HT118 with a 6.5 digit Agilent 34401A. I could use my Solartron 7150P, which has a digit more, but it's a lot more cumbersome to remote control, and for verifying a 6000 count meter, the Agilent will be more than good enough. These tests are pretty boring to watch. Most of them run like this one, which verifies the DC voltage. I use my programmable power supply controlled from my PC to run a series of volts or currents and record readings remotely from the Agilent, which is hooked up to measure the same voltage or current as the HT118A. I then watch the video and add the readings from the HT118A manually into the spreadsheets. In this and subsequent graphs, please ignore the apparent increase in error on the most left. As I explained before in other videos, this is a side effect caused by the fact that the significance of just one digit off has an increasing effect on the error percentage the lower the value becomes. This causes an apparent steep rise in the error, which is really caused by limits in resolution and not a problem with accuracy itself. Another thing you will see repeatedly are these two horizontal lines. They represent the specified accuracy for this range, so for example plus minus 0.5% in this case, making it easy to see how the measured accuracy of the HT118A fares against its specification. Quite well, as you can see. Since my remote controllable power supply is limited to 50 volts, I did the remaining parts by hand using a high voltage power supply, which is why there are far less data points. While I can only test to 200 volts, I believe that covers most of the cases where the HT118A will be used. Within that range, the HT118A is a lot more accurate than its 0.5% DC volts, and its millivolt range is even better. Across the whole range, the HT118 is basically within just 0.15% of the Agilent, a very good result. I use the same method for DC currents by programming the power supply to work in constant current mode and using the current in series through both the HT118 and the Agilent meter. But because there are 3 ranges, I need to do this for amps, milliamps and microamps. For DC currents, it's a very similar picture to DC volts. The HT118A stays basically within 0.2% of the reference meter, much better than the specified 1.2%. Note that I only use the Agilent for currents up to 2 amps because the 3441A is limited to 3 amps maximum and I like to stay comfortably below that maximum. For the same reason, I limited the upper range test with the BM869S as a comparison instrument to 8 amp max. I'm a bit disappointed with the HT118A performance in the milliamp range. The error curve should be a bit flatter, but of course it's still well within spec. In the microamp range, the HT118A is much better, with a flat curve staying below 0.2%, which is a brilliant result for such a meter. And here are the plots for AC volts and AC millivolts. The spike here is at 6 volts when the HT118 switched to the next higher range. For the first part of the series up to 50 volts, I was using my programmable DC power supply feeding my DC to AC converter, while the rest of the data was using AC mains through a variac. At 60 volts we have another range switch of the HT118A with a slightly greater error, but it stays within about 0.3%, much better than the specification of 0.8. AC millivolts starts badly, but that's partly because of the calculation side effects I mentioned earlier, but mainly because most true RMS measurement circuits won't work properly unless there's a minimum voltage. The HT118 manuals stay sadly silent about this, but for example the BM235 needs at least a signal of 1% of the range. For 600 millivolts that would be 6 millivolts AC. In the HT118A it looks as if a bit more signal is needed, 50 or so millivolts, almost 10% of the range, for the results to fall within specification of 0.8% accuracy. Once it has enough signal, it does perform very well and stays generally within 0.2% of the 3441A. To find out the AC bandwidth, I'm feeding about 1 volt RMS to both the HT118 and the Agilent. Then I'm increasing the frequency in steps of 100 Hz until we see about 70% of the original value left on the display. There, just slightly above 3 kHz. This is in line with most multimeters. Verifying AC current is much more tricky because I have to rely on AC mains as the source, which is of course fluctuating all the time. This makes test runs where you compare readings between 2 multimeters updating at different speeds a frustrating exercise. While one meter has sampled the current and is displaying the result, the mains voltage and hence the current is changing, and the other meter will inevitably now sample and display a different value. The fluctuations are not that large of course, but enough to vary the least significant digits, so you can't expect exact values using this method. With these constraints in mind, the plots for AC amps and AC milliamps look quite reasonable. The HT118A stays within 0.4%, which is certainly much better than the specified 1.5%. To check the resistance accuracy, I use a set of precision resistors as a reference. The HT118A doesn't have a REL mode, but it seems to be compensating the leads anyway. My resistance reference box is using V-shaped resistors with 0.1% tolerance and is never used for anything else than verifying multimeters. That's important because it's easy to destroy a good properties of a reference resistor by subjecting it to high loads. With a maximum error of 0.3% at 10 megohm, the HT118A resistance measurements are a lot better than the ±1% quoted in the specification. For capacitance, I have a couple of references you see here, which I use only for verifying multimeters. However, capacitors with low tolerances are very expensive, so most of my reference capacitors are 2.5 or even 5%. The electrolytics are even higher, but at least for those I used high quality Rubicon caps to have a decent long life with stable specs and low ESR. The gist of all this is that instead of plotting the HT118A accuracy against the nominal values of the capacitors, I use the values measured by my BM869S against the same references. The BM869S is accurate to 0.8% up to 500 nanofarad and 1.5% up to 5000 microfarad. As you can see, the HT118A is well within 1% of that, which is far better than the spec of 4% up to 1000 microfarad and 5% beyond. In diode mode, the HT118A has no problems with 1 or 2 silicon diodes in series. You can also turn on and measure the forward voltage of a single white LED but not 2 in series. In conductivity mode, the meter beeps and there's even an additional red or green LED, but all of this cannot hide that the HT118A is rather slow in responding. A little test explains the mystery of the red-green LED, which is otherwise not mentioned in the manual. Shortening the probes produces the beep and a green light. 10 ohms still does the same. And so does 20 ohms. "30 ohms is just a red light and no beep. 40 ohms is the same. And so is 50 ohms. "60 ohms, and now it's just a value with neither light or beep, and same for higher values as well." A quick test of the temperature measurement using the BM869 as a comparison. Both sensors are in close proximity and within a climate chamber that is still some work in progress of mine, but for this test it will do. I'm showing this accelerated and just looking at how the values compare to each other. The HT118A shows Fahrenheit on the primary display and Celsius on the secondary, and you can't change that. The temperature reading on the HT118A is somewhat slower in updating and seems to be about 1.5 to 2 degrees high, but that could well be caused by the tolerances for both sensors and meters. Going the other direction is pretty much the same. The HT118A is slower in updating during the fast rise of the temperature, but in the slower cooling down phase it tracks the BM869S quite well. Let's have a look at the NCV or non-contact voltage mode. It has two ways of operating. First, I'm using the antenna at the top in this setup using mains voltage. If I bring the blue neutral wire close to the antenna, the HT118A shows L for low, a green light, and beeps slowly. If I use the brown live wire, it shows H for high, changes to the red light and beeps faster. The function key switches to the live test, which, as you can see, demands a single lead. With that, the HT118A can tell you which one is the live and the neutral terminal. Make sure to unplug the other lead when using this. While poking the red lead into live, you don't want to accidentally touch the other lead or have it dangling and make contact with ground and rely on those tiny resistors to keep you safe. In this test, the big multimeter on the left is fed directly with AC mains using the blue leads, and the HT1118 NCV mode indicates the presence of high voltage using the red LED and fast beep. Perhaps surprisingly, it does the same for the blue multimeter, which only shows 5 volts DC on the display. While on the small red multimeter on the right, it also showing 5 volts DC, the NCV mode shows only low voltage and a slow beep. If I use my Fluke tester, we see the expected warnings at the most left multimeter, And the same AC warning light comes on when touching one of the leads of the blue multimeter, while nothing happens on the meter on the right. The reason that the seemingly harmless 5V DC shown by the blue meter triggers both the Fluke meter and the HT118A high voltage warning is that it comes from a switch mode power supply, which leaks through its Y capacitor some of the high voltages onto the DC output. The small multimeter on the right was fed from a linear power supply with proper isolation. I've seen reports where people report that NCV is faulty when it triggers on low voltage DC leads. As you see, it all depends how that DC was produced, and in some cases it should trigger a high voltage warning, just like the HT118A does. The HT118A has a dedicated frequency measurement range, which works nice enough as long as you have a signal that crosses 0. It doesn't work at all for pure DC pulses. I'm using a 5V arm as sine wave for this test and rigged up that little PIC based frequency counter with my modified firmware as control. Starting at 100 Hz. Since the frequency display on the HT118A works differently to the other ranges and in full decades, the bar graph that only goes to 60 is kind of useless for anything between 70 and 99. Anyway, I speed this up a bit. We have reached 10 MHz, which is the nominal end of the frequency range, but the HT118A does not slow down, although its duty cycle display starts to drop. Let's see how far it can be pushed. 24 MHz is too much, but 23 MHz still works, which is more than double what it was supposed to do. Very impressive. The other form of frequency measurement is in AC mode as a secondary display. It takes some minimum signal before that can be done. In this test, I increase the signal slowly until we get a stable frequency display. We get some movement at just about 62 mV, but the value is not correct yet. At 67 mV, we get a reasonable value. That's better than the BM869S, which still displays zeros, until we reach just over 70 mV. In the AC amp range, the BM869S is first in displaying a frequency. It needs about 300 mA before that happens. At about 350 mA, the HT118A starts to show non-zero nonsense frequency values, and it takes at least 460 mA before the frequency approaches at least somewhat the correct value. Even at over half an amp, it's still not stable. Compare that with the rock-solid display on the BM869S. The same happens on the milliamp range, with the HT118A needing over 3 mA compared to 1.4 mA needed by the BM869S. This strange behavior led me to have a look at the burden voltages for the HT118A, which are unfortunately not specified but easy to measure. 70 milliohms in the 10 amp range. That's the SMD shunt resistor of 5 milliohms plus the resistance of the 10 amp fuse. (1.4 ohms in the milliamp range). And 100.4 ohms in the microamp range. The resulting burden voltage for the HT118A are shown in the yellow part of the table. For comparison, I added the burden voltages for the BM869S and the BM235 in the equivalent ranges. The only observation is that the 10 amp burden voltage for the HT118A is quite high compared to the others, while its burden voltage for the milliamp range is actually the best of all three meters. But the differences are small and probably not noticeable. In case you wonder what the burden voltage is, basically the voltage lost by using the meter when doing current measurements. So if you measure a device that draws 100 milliamps using the HT118A, means that 100 milliamps times 1.4 millivolt per milliamp equals 140 millivolts are lost. If your device was powered with 3.3 volts, then only 3.16 volts reach it. That's probably not causing a problem, but for devices drawing more current or using lower voltages it might. In general, you want the burden voltage as low as possible. While knowing the burden voltage of the HT11AA is useful in itself, with respect to the threshold for the frequency display, it does not look as if that has anything to do with it. In both the amps and milliamp range, the HT11AA needs more current than the BM869S to display a frequency, but in one case the burden voltage is higher and the other is lower. So obviously the cause is something else inside the meter's circuitry. In my test of the HT11AA, I only came across one problem, which is common with many auto range multimeters, and that is when you measure DC plus AC at the same time. In this complex setup, all three meters are getting the same square wave voltage of about plus minus 85 volts at 100 Hz. With 50% duty cycle, there's only an AC voltage of 85 volts RMS. At 20% duty cycle, the rightmost meter shows in the dual display that we now have 68 volts AC on top of minus 51 volts DC. The BM235 and the HT11AA show the same values, but of course not simultaneously. You need to manually switch between AC and DC to see both components of this waveform. Increasing the duty cycle to 10% reduces the AC part to about 51 volts and increases the DC part to minus 68 volts. And now the HT11AA is lost in an auto range loop. Interestingly, if I manually look at the DC value and then switch back to AC, it does a fresh ranging from scratch, so to say, and can now settle on the correct range. However, the displayed AC value is not very accurate. With a square wave of 10% duty cycle, we are probably at the limit of the crest factor that can be handled by the true RMS implementation in the HT11AA. Lowering the duty cycle to 1% means we now have almost no AC and a high negative DC voltage of almost 85 volts. Increasing the duty cycle back to 5% and we should see a DC value of minus 75 volts and an AC value of 40 volts, but both the other two meters are now caught in a false range setting and showing only about 1/10 of the actual AC value. That could be quite dangerous. And while the BM235 can be rescued by a cycle to DC and back to AC, or switching to manual range for that matter, nothing works for the HT11AA. An increase to 12% duty factor finally fixes the HT11AA because the DC content dropping from the 600 volt range to the 60 volt range, thus causing an automatic range change, which now suits both the AC and DC content. To be clear, this is a very tough situation for any multimeter, and as you can see, it's not just the HT11AA that struggles with AC riding on top of DC when the values for both fall in different range brackets. It's more vulnerable though, because it does not allow manual ranging to override auto mode when that gets it wrong. So what's the conclusion? For a meter of the $30 or pound class, the HT11AA is a pleasant surprise. It's actually way better than the specification, or at least in my case. Of course, there's no guarantee that all meters are like that, but even the guaranteed specs are reasonable for an entry-level meter. It has a few niggles. Slow continuity and slow pickup of the correct AC frequency when measuring currents are the main ones. The frequency measurement range is impressive, but would be even better if it did not need zero crossing signals to work. That rules it out to measure frequency of digital logic signals unless you add a coupling capacitor. The leads are quite decent and the display is easy to read from a wide range of angles. I particularly like the max-min button and that the backlight stays on as long as you want and that the automatic 15 minutes power off can be disabled. The unique point of the HT118A is of course its light show. Showing the right terminals to use and warning of possible dangerous voltages and currents is useful especially for beginners. Sadly, especially beginners would really benefit if the HT1188 would sense whether the leads are indeed plugged into the right terminals. As it is now, if you ignore or miss the hint given by the lights, you will still blow up your meter, or at least its fuse, when leaving the leads in the amp setting and trying to measure voltage. Finally, although the meter claims 1000 volts Cat3 and 600 volts Cat4, the fuses are only rated for 250 volts and there's very little other input protection, making it vulnerable to transients and spikes. I do not recommend using this meter for anything else than normal electronic workbench stuff and maybe routine household mains measurements like at sockets on light fixtures, but not for measuring inside power consumer units, switchboards or large electric motors. Last not least, you can now support the channel by becoming a Patreon. If you do, you get early access to videos as well as additional exclusive content. Thanks for watching.